Hello, today we are going to start with mixtures. There are two types of exercises. The first starts with a weak acid or base, and then we add a strong acid or base. And in the second type, we initially have a weak acid or base, to which a salt is added. Let's look at the first type. Imagine we have a weak acid, for example acetic acid, written as HAC. The pKa is 4.75 and the initial concentration is 0.05 molar. This acid is monoprotic, only has one proton that can be liberated to the medium. Therefore, the logarithmic diagram only has two species coming from the acid in it. As the initial concentration is of acetic acid, we are in the left part of the diagram, where the concentration of HAC is maximum. If we look at the lower vertex of the triangle, the pH is 3, so the initial pH of the solution is 3. We can add a compound to increase the pH to make the solution more basic, or move the pH to the right part of the diagram. These three sentences are the same concept. To increase the pH, a strong base can be added, such as potassium hydroxide, KOH. The final pH obtained after adding this strong base will depend on the amount and concentration of this strong base. There are certain characteristic points in the logarithmic diagram, the crossing points between different lines of the species in the equilibrium. They have specific meanings. The first crossing point is the one defining the initial concentration and pH of the weak acid in this case. There is another crossing point in the left side at a more acidic pH. To get to this point, a lot of strong acid should be added, not a base, because pH needs to decrease, go to the left side. On the other hand, if we add a strong base, as in this example exercise, the pH rises and we move towards the right part of the diagram. The first point we encounter is the one where the pH is the same as the pKa. In this point, the concentrations of both weak acid, acetic acid in this example, and the corresponding anion, acetate anion in this case, are the same. They have the same concentration. If more strong base is added, we find the next point with higher pH. And finally, there is one point left at very basic pH. In this case, this pH is attainable when the starting point is a strong base, or by adding a lot of strong base, so that the amount of strong base is much higher than the amount of weak acid. These characteristic crossing points have a special nomenclature. The F factor can be defined as the concentration of the strong acid or base added divided to the concentration of the weak acid or base we start with. These are the three significant points in the case of a monoprotic acid. The ones in the extremes are not considered as they correspond to predominance of strong acids or bases. So let's go back to our exercise. When no strong base is added, we are in the initial point, F equals 0. When strong base is added, gradually we are moving to the right part of the diagram until the next point, F equals 0,5. Here the concentration of the strong base is half the concentration of the weak acid. If we think about the chemical equilibrium, half of the concentration of acetic acid has turned into acetate anion. If we keep adding strong base, we reach the point F equals 1, where the concentration of strong base is the same as the one of weak acid. Now, all the acetic acid has turned into acetate anion. What we should learn from this exercise is that then increasing the pH of the solution of acetic acid by adding a strong base, such as potassium hydroxide, causes the equilibrium to switch. We move into the right part of the diagram, where acetate anion is predominant. This is the basic species, the one predominant at a high pH, which is basic pH. Now let's look to another case where the starting point is sodium acetate 0.05 molar. The salt dissociates totally and we have 0.05 molar of acetate anion. Therefore, we are in the right side of the logarithmic diagram. The pH of this solution is 8.8, basic or alkaline pH. If we add a strong acid to decrease the pH, such as hydrochloric acid, again we will go through different characteristic points going left in the diagram. Again we have defined the F factor, and in this case the F equals 0 is in the right side, in the lower vertex of the triangle of the area where the concentration of acetate is the maximum, the initial concentration. Here, no hydrochloric acid has been added yet.
When adding some strong acid, some acetate ions will start to turn into acetic acid while gaining the hydrogens from the acid added. Then we will reach the point F equals 0.5, where half of the initial concentration of acetate has turned into acetic acid. In this point, the pH is equal to the pKa of the substance, the weak acid, acetic acid. In this point, the concentration of acetic acid and acetate anions is the same. If more strong acid is added, F equals 1 point is reached, where all the acetate ions have turned into acetic acid. We can see that the pH of these points is lowering while going to the left side of the diagram. With this example, the equilibrium switches, moves into the left part where acetic acid is predominant, is the acidic species, the predominant at low pH, acidic pH. Let's do a summary with a more complicated example, with a diprotic acid. We have a logarithmic diagram of carbonic acid. On the left, the more acid species, and on the right, the more basic substance. We can start from any of the species and add a strong base or acid. Let's take a specific example. We start from sodium carbonate. If we only have sodium carbonate, we are on the right, and in the inferior vertex, which is the cross point between the OH and the hydrogen carbonate, it's equal to F equals 0. If we add some acid, we move to the left. Every time we add acid, we move to the left. We can add different acid concentrations. If we add it drop by drop, we will reach a new characteristic point, which is F equals 0.5. If we keep adding acid, we get to the crossing point between carbonate and acid carbonic, which is F equals 1. The following characteristic point is the crossing point of acid carbonic and hydrogen carbonate, which is 1.5. And the last point is a crossing point between H plus and hydrogen carbonate, which is F equals 2. In the current slide, we have a short summary of what we've mentioned before. We see how the different F's move along the logarithmic diagram. If we had added base and we had had an acid at the beginning, the F would be equal to 0 and would have increased as we would have moved to the right. This is a very characteristic table. What can we directly see or deduce from the F values? Let's start with 0. If we have 0, that means that there is no strong acid, chlorhydric acid in this case. The predominant species is carbonate. The dismissed species are the ones underneath, H plus and carbonic acid, and the species point of the diagram is the crossing point between the OH and the hydrogen carbonate. In the second row, we have F equals 0.5. The crossing point in the diagram is carbonate with hydrogen carbonate. Initially, we only had carbonate, but now half of it has transformed into hydrogen carbonate. In this case, the predominant species are carbonate and hydrogen carbonate. The rest can all be dismissed. Have a look at the rest of the table and try to understand it as much as you can, so that you can be able to do it at any given time. The F factor will always be the concentration of the strong species divided by the weak species. Now let's have a look at the second exercise, where we mix a weak base and its conjugated base or acid. First of all, we have to calculate the new concentrations. We mix 0.2 liters of acetic acid, 0.1 molar, with 0.3 liters of sodium acetate, 0.02 molar. The methodology is always the same. First, we calculate the total volume. They are going to be considered additive volumes because the concentrations are very little. They can be added directly with a very small error. Then we're going to calculate the new concentrations after mixing. The formula is number of moles divided by volume. In both, we calculate the number of moles and we divide by the total volume. These concentrations are the ones we are going to use throughout the equilibria. We start from both products, a completely dissociated salt, and we have the concentrations of sodium cation and acetate anion, which are 0.12 molar. For the mass balances, the sodium cation will be constant throughout the process. The acetic acid will be very important. We have two different initial concentrations. The acetate initial concentration is 0.12 molar. That comes from the dissociation of sodium acetate, and the acetic acid concentration 0.04 molar that comes from the initial concentration of the acid itself. The addition of both equals the concentration in equilibria. To solve this problem easily, we have to think where we are. Given that it's not only one species, we're going to find ourselves in the crossing point between the two of them, which is indicated by the yellow line. The H plus and the OH minus are dismissed since they are 1.3 logarithmic units underneath. This indicates that the acetate equilibria is the same one as the sodium one. From the second mass balance, we get that the equilibria concentration of acetic acid is 0.04 molar. We write the equilibria and associated constants. We know all the data in the equilibria of acetic acid except the H plus concentration. We calculate it, and from it we can calculate the pH, which is 5.23. It is found slightly to the right of the crossing point of both species. Therefore, having the pH or the H plus concentration, which is the same thing, we can calculate the concentration of all the other species, substituting in the equations. So now we have to find the F factor as a strong species concentration divided by the weak species concentration. It is important to specify that they are the final concentrations, which are the concentrations that we have recalculated after we have mixed. In this logarithmic diagram, we can see the pH of 5.23. In the next slide, we can see the different concentration of all the species with its unit. In this case, it's molar. Again, this slide and this information is very important. Please don't forget. Now, we're going to start with buffer solutions.
A buffer solution can handle small additions of acid or base without changing its pH much. We have several buffer solutions in the environment, for example in our blood, to maintain a constant pH in our body. We are going to see how to produce this buffer solution using the logarithmic diagrams to help us understand the chemistry behind it. We will work with a known system, acetic acid. Here we have the logarithmic diagram of acetic acid. This acid has a pK of 4.75. When the concentration of the two species in the equilibrium are the same or very similar, the system is a buffer solution. In this case, we have a buffer solution when the concentration of acetate anion is similar to the concentration of acetic acid. But how similar should the concentrations be to be a buffer solution? 1 unit of pH lower and 1 unit above the point of crossing of the two species, the point where the pH is equal to the pK. Imagine we have a sodium acetate solution 0.05 molar. Is this a buffer solution? Clearly not, because we predominantly have acetate concentration, and the acetic acid concentration is negligible in front of the other one. Let's see an example of how to achieve a buffer solution if the starting point is a sodium acetate solution 0.05 molar. In this case, we are in the right part of the diagram. What should be done to move into this buffer solution point? This point is at the left part of the initial point. Therefore, the pH should be decreased. To do so, an acid must be added. At this point, the buffer capacity is highest, and the solution will be able to equilibrate, neutralize the addition of acids or bases. The pH won't change much when we are at this point. Let's try to get to this point. So we were saying we start with a solution with acetate concentration 0.05 molar. We are in this point of the diagram. Remember, F equals 0 as no strong acid has been added yet. And we want to go to this other point, the point where pH is equal to pK, and the point where the concentration of acetate anion is equal to the concentration of acetic acid. This point is ideal, with the maximum buffer capacity, but actually, around this point, it is also a buffer solution. To do this, acid should be added to the solution. A strong acid, for example, this one. Do you remember its name? It's hydrochloric acid. So, how much of this acid should we add to get to the desired point? An amount such that in the equilibrium, the concentration of strong acid is half the concentration of weak base. Remember, the weak base is the acetate anion. It's a base because it can catch protons. At this point, half of the acetate anions have turned into acetic acid. Do you remember the concept of F factor? In this buffer point, the F is 0.5. If the hydrochloric acid is very concentrated, 1 or 2 drops will be enough so that when adding them to the solution has a final concentration of 0.025 molar. This final concentration is the equilibrium concentration. To do so, we would need to know the volume of the initial sodium acetate solution and then calculate the necessary moles of hydrochloric acid that we should add. These moles are in these drops that we add. We can say, therefore, that the volume of solution is constant because adding these small drops practically does not vary the total volume.